And hello, welcome to this video. So in the last video we were at this sort of YouTube demo tool, and yeah, I think as of today there's some update for DWSim, but I decide not to update because I want to go straight into content, and today's content is going to be about recycle streams or recycle loops, and maybe hopefully we give you some idea how they work. So I'm going to save this file as YouTube demo 3, and I'll name this recycle blocks. Okay. Why do we need recycle blocks? Yeah, it's a little hard to understand why we need recycle blocks without having some knowledge of code and how things work with code. Okay, so if I have to assume you have taken some computational methods class where you learn how to design code that solves equations iteratively. So I assume you have taken that. That's a prerequisite knowledge. For this part of the tutorial, or rather the walkthrough. Okay, I'm still rusty with DWSim, and as I relearn or learn, I will just make videos. That has always been the style of this channel. Okay, so let's open LibreOffice. Okay, so I assume you know how those things work. You have to know how those things work. It's a very basic engineering thing. So I'll just save this as a demo file or sketchpad or something like that, right? So I just put it in desktop, sketchpad. Okay, it's just for us to do some demonstration. So what I'm saying here is that you cannot just hook this arrow up to this arrow and wait for the DWSim to solve everything until everything reaches steady state. Okay, so how do we then do it? Okay, so let's start. Okay, so usually for a code to run, okay, we usually for this diagram to be solved, you have to imagine these blocks, like bits of code. So for example, the terminal stream inlet here, it will be a bit of code. Terminal stream inlet, there will be a certain temperature, a certain pressure, a certain flow rate. Okay, so this will be the terminal stream inlet. Then you have a pump. Okay, so the pump in will be the terminal stream inlet. So we'll call this T1, P1, and this is F1. Alright, so what am I doing here? I'm saying that the terminal stream inlet, which is I'm saying that the terminal stream inlet, which is this stream right here, it actually has some variables attached to it. For example, the temperature, pressure, and flow rate. Just give you an example. And the pump isn't actually, you don't simulate the full pump. Okay, a pump is just, well, in the context of DWSim, of course it looks like a pump here. The diagram looks like a pump. But what's going on behind this terminal pump? This terminal pump is just an equation. So for example, over here, we actually dictated that pressure must increase. Okay, our condition is pressure increases by 100,000 pascals. So the pump in the sense of the code, okay, the pump in the sense of the code is going to take these properties and then it will add something. Okay, so at the pump outlet, okay, if it's a perfect pump, if it's a perfect pump, then all the pump does is this. That means it's 100% efficiency. Okay, it's a 100% efficiency pump. What it does is this. It will just take these values and then, okay, this is the change. This is not the condition. This is the change that we need to do. It says pressure increases by 100,000 pascals. Okay, so let's take whatever value that's here, and then we add 100,000 pascals to it. And this is simple enough. P2 equals to P1 plus 100,000, and T2 equals to T1, and F2 equals to F1. Where F2, T2, P2, and F2 are the temperature, pressure, and flow rate of the flow coming out of the pump. Of course, we don't simulate actual fluid flowing here and there. We just represent them with these numbers. The temperature, pressure, flow rate, and all the other things that you do. So behind this pump is just a block of code running, and it adds some pressure to the pressure here. If it's not perfect, right? If it's not perfect, then then the temperature will increase as well. The temperature will increase. So I say T increase because oh wait, I shouldn't put it here. Okay, let's put a different one. At pump outlet, if not perfect, then yeah, it means that the pump efficiency is not 100%. Then what we'll need to do is you will actually add some increased temperature to the flow because you're adding some heat to it. So you can see here from 25 degrees C it becomes 25.03 degrees C. The flow rate in and out is the same. Okay, so all the pump here is doing is taking the values here, and then there is some function that changes the values T1, P1, and F1, and then it just adds it accordingly to the temperature, pressure, and flow rate. And basically every step of the way, or rather every component here, is just a function that does the same thing. So for example, the terminal outlet pipe, okay, so here we say this is MSTR02, right? MSTR02, this is material stream 2, temperature, pressure, it's like so, T2, P2, and F2, where T2 is the temperature of this MSTR02, which is represented by T2, pressure is represented by P2, and flow rate, mass flow rate, okay, let me just be clear, mass flow rate is represented by the number F2. So this is MSTR02, which will be taking all the values from here. So this is how the pump calculates all these properties. Then MSTR02 will go into a pipe, right? Okay, MSTR02 will go into a pipe. We call it the terminal outlet pipe. We just name it like such, as such. Then at the inlet, we will have T equals P2, T2, P2, and F2. And then what's the change here? Okay, I will lose some pressure. I'll lose some pressure due to a pressure drop or hydraulic profile, as you saw in the last video. I hope you still remember. If not, yeah, you'll do this. You see the hydraulic profile here? We actually represent it by some straight tubes, elbows. So you have to lose some pressure or gain some pressure according to your pressure drop or hydraulic profile. Alright, so you lose or gain some pressure, and then of course you can lose or gain heat. So this is based on the temperature profile. Alright, so based on whatever that your profile is, your outlet at the outlet, the temperature, the pressure, and the flow rate will change accordingly. But of course, in our case, for the flow rate, okay, we call it F3, to represent the flow rate that's coming out of this terminal outlet pipe. So this is for MSTR03. Yeah, but the flow rate that's coming out, F3 equals to F2 in terms of mass flow rate. The pressure P3 equals to P2 plus whatever change, or minus P drop, pressure drop, because well, pressure drops as you flow through a pipe, or maybe pressure can increase as you let's say go upwards in a pipe. So there's some hydrostatic pressure change. Likewise, the temperature, it can increase or decrease based on a change depending on what kind of fluid it is, and all that is actually determined as if this was a function. So again, all the terminal outlet pipe is doing is taking these inlet variables and you pump it through a function, and then after that it churns out these outlet variables. So that's what this what's going on behind the code. Then after that, finally you get MSTR03. Okay, MSTR03. Then temperature, pressure, and flow rate will then be T3, P3, and F3. Now, if you look at it, if you look at this flow sheet as if it's a line, a series of code being executed sequentially, it'll be easy to see why we cannot just hook MSTR03 back to the terminal stream inlet. Because to get MSTR03 in the first place, you need to have a certain set of inlet conditions to start the calculations. Then once you have this set of inlet conditions, you pass it through the functions of the pump. Okay, the functions of the pump will take in these inlet variables, you'll change it, and then you will have some output over here, which is MSTR02, or at least the properties here. Then same thing for the pipe. So once you calculate MSTR02, the properties of it anyway, then you put it through the terminal outlet pipe, and then you sort of get the conditions or the variables for MSTR03. Only when you have MSTR03, then so-called, if you want to calculate a steady state for this entire system, then you need to say, then you need to somehow copy and paste these values, T3, P3, and F3. You need to copy and paste them back to this T1, F1, P1. So what do you do? Okay, you have a block of code here called the recycle block. Okay, recycle block means what does it say? It connects this terminal stream inlet to MSTR03, terminal stream inlet to MSTR03, and what does it do? Okay, what it does is here, you have the temperature, you set. Okay, the function is this function. Okay, the inlet is here. The temperature is P3, pressure temperature is T3, pressure is P3, flow rate is F3. So the function is this. Okay, set T1, P1, F1 to be equal to T3, P3, and F3. So that's the function. So remember, what we are doing here is just applying a function to these variables, and then we will churn out the output. Okay, so the function is to set T1, P1, and F1 to T3, P3, and F3. Roughly speaking, the function is like that. I may be wrong exactly how it works, but this is the idea of how a recycle block actually works. So the recycle block is like any other what do you call that, function or any other module. So this module will take the sets of variables from this input and then run it through a function and then churn a specific set of outputs. Same for this pump. So to actually connect this loop together so that the flow is cyclical of some sort, then you will need to have this recycle block. It does not even matter if this system is physically possible, because somehow this pump is actually just increasing the pressure by 100,000. This pipe is actually, if you take a look at the profile, is actually moving upwards. Okay, so in order for, realistically speaking, for the flow to come back to the pump, you need to have the flow moving downwards again. So yeah, I think I mentioned just now that was a mistake. When I said fluid flows upwards, like the pressure will increase, no, it should decrease. If the fluid flows downwards, and the pressure will increase. So I think I must have made a mistake back there somewhere. But anyway, yeah. So if you caught the mistake, good for you. Very good. Then you're attentive. Okay? I'm just trying to explain some things. But I think I'm kind of fumbled here and there. But anyway, so what you need to do to connect the loop is to introduce another function that sets T1, P1, F1 to be equal to T3, P3, and F3. And then you repeat the cycle over and over and over again. Okay. Of course, repeat until iterations of T1, P1, F1 equal T3, P3, and F3. Now this is specifically like what's supposed to happen. So you can see MSTR03. What's the temperature here? What is this? Yeah. Okay, good. The thing was disappeared. I want it to disappear. Now you see the flow rate is 800 kg an hour. Here's the flow rate is 800 kg an hour. However, over here the pressure is 189,000. All right, 189,000. The temperature is 25.03. So on and so forth, right? Okay, so what's going to happen? Okay, so if we cycle this back, okay, if the recycle stream works like this, we set T1, F1, T1, P1, and F1 to be equals to this value. That means the terminal stream inlet on the next iteration will be 25.03. The pressure will be 190,000. The flow rate will be the same. Then we'll subject it to the pump again. The pump will actually increase it by 100,000 over here. Okay, and then of course the temperature will again increase slightly. Then you put it through the pipe where you will have some pressure drop and very minimal heat loss. Very minimal heat loss. So there's a little bit of heat loss, but it's not even enough to cool the thing down, because probably we have very good insulation. Okay, and then after the thing gets a heat loss, then likely we'll have MSTR03 with maybe 25.06, about 290,000 Pascal, or maybe slightly less, and then 800 kg an hour. So if you keep this loop going, you can see that the values don't really settle down. I mean the pressure will just keep increasing exponentially. So that's not good. Okay, what you want is, the goal of having our recycle loop is to have MSTR03's pressure to be equal to the pressure over here, MSTR03's temperature to be equal to the temperature here, so that we have we solve for a set of flow conditions that satisfies this steady state where you have flow going around and around this loop, right? So that we will have some form of steady state that actually makes sense. Okay, so again, what we want at the end of the day is we want to have a set of flow conditions. We want to have a steady state flow through a pump and then a pipe, right? We want to have a steady state flow through a pump and a pipe, and that's what we want, right? And then question is, what are those steady state conditions? What will the temperature, pressure, and flow rate be at each of these parts? So to get the temperature, pressure, and flow rate at each of the parts of this stream, you have to solve the equation iteratively, and that's why you need this logical block called the recycle block to help you do that. Now, it doesn't mean that just putting a recycle block there will solve it for you. You have to set your functions here such that the values will converge, and this is sort of an art and a science as well, because it's if your recycle block doesn't converge, you have to kind of find the reasons why it does not. Maybe you over specify your system, maybe like what I described just now. You have this perpetual increase in pressure that's really unrealistic. So yeah, you don't really know, right? The pressure of this pump will just keep increasing and increasing and increasing to no end. So that doesn't make sense at all. Okay, so instead of that situation happening, what can we do, right? What can we do? Okay, well, we'll have to find out and get our hands dirty. Okay, so bear with me. We've gone through the basics of how this whole block works, and now you know why you kind of need a recycle block. Yeah, now you kind of know why you need to have a recycle block. So let's try putting a recycle block here. Okay, and like I said just now, the likelihood, if we keep this thing iterating, the flow solutions will not converge. You'll get some really strange values, and they'll probably run into an error. So you need to set your system such that you don't have this kind of situation happening. But let me demonstrate to you what happens first if you just connect the recycle, if you just connect the arrows without thinking. Okay, and this is a very common, I guess, beginner mistake. It's quite normal. So the inlet stream will be this MSTR03. We can use a global convergence Broyden whatever. Okay, and then you set the outlet stream to maybe a terminal stream inlet. Okay, likelihood you will get an error if you run the soft flow sheet. So you can see that after a few runs, we will actually have very weird values like minus 3737.42 degrees C, right? Because we made such a, let me exit this, very distracting. Yeah, we made what do you call that? We made a system that doesn't really make sense at all. That we just keep putting in, we just keep adding pressure higher and higher. That after each loop, it will keep this terminal pump will just keep adding pressure. So, is it realistic that a pump will just keep adding 100,000 pascals every time you push it through the pipe? It may work, it may not work, right? Maybe instead of 100,000, you just give a fixed 30 Pascal increase. Okay, and then again we'll set this as maybe 298.25 degrees C, 1 atmosphere, and then maybe we can solve the flow sheet like that. Okay, solve flow sheet. Okay, maybe I'll delete this first. Let's solve the, right. 25 please. Okay, so now everything's going to work. Now you see that the pressure here is set down to less than 1 atmosphere, so it doesn't really make sense. Okay, now if we keep running, if we increase this pressure by so low, every time you cycle through the loop, the pressure is going to drop, and then maybe it even goes negative. So is this thing going to work? maybe not. So maybe we should to get this to converge properly, what we need to do is to maybe find a different kind of function. Okay, find a different kind of function that like for over here. Over here we set the function such that the pressure increases by a set amount every time. Now if we do that, sometimes the solver will just become very unsteady. Okay, become very unsteady, and then the pressure over here will just be set at this amount, 88,000 blah blah blah, and then when it comes back here it will add maybe 30 pascals, and then it goes down here, it drops by I don't know how many 10,000 pascals again. You'll keep seeing the pressure drop. So that is not really a good way of doing things. So instead of doing that, instead of setting a set pressure increase, we can instead set maybe this we can set a fixed outlet pressure, and this will help instead of this will help this whole flow solution have one set of fixed points. So let me illustrate. 130,000 pascals maybe here. Yep. So no matter how what this does is that if we set the outlet pressure to 130,000 pascals on this pump, no matter what the inlet pressure over here is, the outlet pressure here will always be 130,000. Doesn't really matter, right? So no matter how we iterate, here we will have a pressure of 130,000 pascals. Now, in this case, doing the recycle stream thing will be much easier, because no matter how we iterate, this part will become sort of fixed. And this is actually a good starting strategy to help you iterate such that your loops don't like go numerically unstable. Okay, so you have to be very familiar with what numerical stability is for solvers. Okay, in order to understand this recycle stream part. So let's solve the flow sheet, and this time it should work nicely. All the values should converge. Okay, so you see that the MSTR03 25.01 degrees C, 118,000 pascals, and then the terminal stream inlet has to be set to be equal to this within a certain tolerance, of course. And then you put it back into the terminal pump, and then what the terminal pump does is that it just increases the pressure to 130,000 pascals here, no matter what the pressure here is. Okay, so this is just a demonstration of, and hopefully some explanation of how this code actually works. Right? You can look at this thing again. Just imagine that each stage of this flow sheet is actually basically, these are just variables. You put them through a function, okay, that may or may not reflect reality. Okay, but these are just variables. You churn them through a function, and then it churns out a set of different variables here. And then when you go through a different component of the loop, it's the same thing. It's just a function that takes a set of input variables. You put it through a function that you define based on what you do here. You can specify outlet pressure, you can specify outlet temperature, and then it will just churn out a set of variables here. Then if you put a recycle stream here, recycle block here, you will just keep going round and round and round until it will keep trying to solve, and it will keep iterating until MSTR03 and terminal stream inlet are essentially the same. Then you will know what is your steady state solution. So there is a little bit of art in getting these recycle streams to converge. May not be the most straightforward of things. It kind of I think requires a few examples for us to get used to. But hopefully this example is good to help you get started. Alright, so yeah, next time you run into errors like this, you can sort of break down what's going on in the flow sheet as if it were a set of code like that. Think through what is going on at each step, and then just run through in your mind. Okay, at the first iteration, what is actually going on? What are the values being put into each section? So for example, these are the input values that go into the pump. Then you churn this set of output values. Then it will go through this this pipe, which is actually just in fact a set of mathematical functions that manipulates these inlet variables to give you these outlet variables. And then once you put the recycle stream, this set of variables here will be set equal to this set of variables, and then you just keep going round and round and round until you iterate it. You iterate it such that MSTR03 hopefully will equal to the terminal stream inlet eventually, within a certain tolerance. So this is what we are doing here. It's just numerical solving, iterative numerical solving. So next time you run into errors like this, just run through what's going on in the loop in your head. Alright? And then hopefully you will find the reason why it gives you a problem. It's not the easiest thing to solve. It will take some detective skills, but that's part and parcel of learning DWSim or even other commercial software as well. Okay, next thing is that you'll notice that this system is not physical at all. So just because your flow sheet here converges doesn't mean it reflects physical reality. So I'm actually putting a terminal stream through this pump, and this pump is actually pumping a hydraulic profile upwards, right? If you take a look at the hydraulic profile, I actually have a section of pipe that's going upwards and a section of pipe that's going straight after a bend. And then after that, it goes into this flow, okay, MSTR03. Then it has to go back here again. Now the flow sheet is not going to check for you whether this situation is physical. You have to perform your own checks, and yeah, you really have to perform your own checks and see whether does it make sense. Okay, you have to see whether it makes sense for you. So yeah, you have to see whether it makes sense physically at each stage. Okay, and for example, okay, you see this MSTR03 is 25.01 degrees C. Okay, you check the temperature here. This is another physical phenomena you may or may not see. This temperature here is 25.0109. Okay, so just now I explained that the fluid flowing through the pipe and going through height increases and all that, it may not be physical because the fluid, once it goes up here and goes to this material stream here, technically you're supposed to have another section of pipe that brings it to the correct elevation and goes back down to the terminal pump. Okay, the flow sheet isn't going to help you see that. You have to sort of visualize that on your own. Maybe draw something that makes it physical for yourself. Alright, so that's one thing about physical reality, that even though the everything can solve, it doesn't mean that it's physical. And then the other thing that may or may not be physical is you take a look at this temperature increase. This is 25.0109 degrees C. What's this temperature here? 25.0109. This temperature here is 25.0127. Okay, 25.0127. Okay, so if we keep clicking this soft flow sheet, you keep clicking this soft flow sheet, you can see the temperature will keep increasing at the successive iterations. You know why? Because we are actually putting in energy through the terminal pump. Okay, we are putting energy in through the terminal pump, 0.00325 kilowatts or 0.032 kilowatts, and then the energy lost here is still not really there yet. So you see this energy lost through the pipe is actually 0.00246. So there's more energy being put into the loop than is being taken out. So actually the temperature is not converged yet. Okay, so this again doesn't reflect a true steady state. It just so happens that the tolerance here, the tolerance here was 0.1. Okay, the tolerance here is 0.1. So as long as the temperatures here and here are within 0.1 degrees of each other, the recycler will think, okay, this thing is kind of steady state already, so I don't really need to care. I will assume this is solved. Now this may not be true, especially for this case. Okay, you have to check whether the energy flows in and the energy flows out of this loop are equal. Only when they're equal, then you can say truly, yes, then the flow kind of stabilizes. So if you that's the other physical thing you need to watch. Once your mass balance, once your energy balance. Okay, and just now we were talking about energy balance in terms of height, and now we are talking in terms of thermal energy. So you got to think about these things. So at least for temperature, to make it more realistic, we can set the tolerance to be really, really low. Instead of 0.00245, we can set the tolerance to be much lower, maybe 1e minus 0.06. Alright, and then I'll save this, and then let's solve the flow sheet. Okay, then it should go over a few times until it solves. So you can see that now, 25.15. Okay, after 50 iterations, it will stop. And what happens? It says recycle reach maximum number of iteration without converging. Right, so you see the maximum iterations here is actually 50. Right, there's a 50 iterations. So you must know that, okay, this recycle loop doesn't go on indefinitely. You set a set number of iterations, then you'll stop. Okay, so you take a look here, the energy flow out is like what, 0.00249, whereas the energy flow in is still 0.0032. So it needs to go on a few more times in order to iterate properly. So if you want to change the iteration number of iterations, you can use this, and you can check this global convergence Broyden just to alter what's in this recycle loop. So maybe we can have 100 iterations, for example, and just to help this thing converge a little faster, maybe we'll just put this thing at about 30 degrees C, right? We shift the thing ahead. So let's solve the flow sheet. So it will go through 100 iterations, and then we will have some kind of a problem. Okay, we have negative temperatures. Why do we have negative temperatures? Let's take a look at the energy balance. Okay. Yeah, clearly something is pretty off. Okay, maybe I set the temperatures wrong. So we have a similar problem to what we have just now. Basically, we set we set this in terms of a thermal energy balance. We have a set amount of energy going into this pump. Okay, in terms of thermal energy, and then another fixed set of thermal energy coming out of this pump. Okay, if those two don't balance, then technically this system will keep accumulating heat over and over again as we go through the iterations. Yeah, then you will have this non-converging temperature issue as well. So somehow you will need to ensure not just the pressure the pressure variables, not just that you don't just have to stabilize the pressure variables. If you want to get the temperature thing right, you have to stabilize the temperature variables as well. Okay, so of course you can set the tolerance to be really, really low, like 0.1, or rather the tolerance to be high, like 0.1, but then you won't have a physical system. So these are some of the things you need to take note. It's not a one-size-fits-all answer. You have to go through a thinking process in order to deal with this recycle blocks. Okay, so I think that's enough for one video. I've gone through a fair bit. It's almost 40 minutes, as you can see. So I'll stop for now. I hope this helps you understand what's going on behind these recycle loops. and hopefully you will be able to solve your flow sheets well, and also you will get a physical realistic answer. Okay, so thanks for watching. I'll see you.